Hi, my name is Fabien Dufoulon, and I'll be talking about this work, Can Uncoordinated Beeps tell stories? This is joint work with Janna Burman and Joffroy Beauquier from Université Paris-Saclay. First, what are beeps? Well, they're the simplest communication signal possible. Beeps transmit no content, the only information they transmit is the fact that someone communicated. More concretely, a beep can be a burst of sound, a burst of light, or a burst of wireless energy. Such a weak communication mechanism is interesting for several reasons. First, it is general. Second, it is surprisingly efficient. Leader election solutions designed using beep have been shown to be optimal in stronger settings. Finally, better understanding the beeping communication mechanism may help us better understand distributed systems that emerge from natural phenomena. This is because these systems also use extremely weak communication mechanisms. Beeps were introduced in the distributed computing community in 2010. Ever since then, there has been many studies trying to understand what beeps can or cannot give you in a distributed setting. We are also interested in this question, but the question we really ask is what can beeps give you in a harsh distributed setting? In this presentation, we will first give the uncoordinated beeping model. In the second part, we'll define the two-hop desynchronization problem. In the third part, we'll give some technical tools, which we will use in the fourth part to implement the two-hop beeping primitive and to solve the two-hop desynchronization problem. In the uncoordinated beeping model, we have a communication graph G. Its nodes represent devices, and its edges represent whether two devices may communicate with each other. Now, we assume that nodes have no knowledge of the graph, except for some up or down on the maximum degree. Nodes are not restricted in memory or computation, but have no unique IDs. We assume that time is divided into discrete time intervals called rounds. In each round, nodes execute first computation step, that is, depending on past information, they decide to listen or beep. Then in the second step, accordingly, they listen or beep. If a node listens, then it knows whether at least one of its neighbors beep. Here we have an interference phenomenon. Otherwise, if a node beeps, then it receives no information during the round. We assume nodes have no access to a global clock. We call this setting the uncoordinated start setting. More precisely, nodes wake up in some arbitrary round. Importantly, they do not wake up upon hearing a beep, and as a result, two neighboring nodes may have arbitrarily different local round values. Due to the uncoordinated starts, we have a complex round structure. On the one hand, we have global rounds, which are determined by the first node to wake up. And on the other hand, each node has its own local rounds, determined by its wake-up round. The local round of node V is denoted by RV. The corresponding global round is denoted by GVRV, and this GV function is only used in the analysis. It is not available to nodes. In the example below, node V is asleep in the first 49 rounds. In global round 50, it wakes up. This is its first local round. And then it just increments its local round in each round, but it does not know which global round corresponds to these local round values. We define the history of node V from round RV to RV plus T for any integer T as follows. This history is a sequence of beep or silence information received by the node over T plus 1 consecutive rounds. If V beeps in some round R, then in the history for round R, there is a beep information received. Now, if V listens, but some of its neighbors beep in round R, then in the history, there is also a beep information. And this is also the case no matter how many of its neighbors beep or which of its neighbors beep. Finally, if node V beeps in round, it listens in round R, and none of its neighbors beep, then in the history in round R, node V has a silence information. This is an extremely harsh distributed model. In this model, we're interested in studying the two-hop desynchronization problem. The two-hop desynchronization problem is a variant of two-hop coloring. Instead of choosing different colors, nodes choose different global rounds. More precisely, nodes output a periodic schedule of global rounds which are exclusive within distance 2. This schedule should be periodic with known period T. And a two-hop desynchronization solution is interesting because it allows nodes to control interference. It allows nodes to beep in rounds in which their neighbors do not. Here, a two-hop coloring cannot control interference in this setting, this uncoordinated task setting. And this is because nodes have arbitrarily different local round values. They cannot properly use a two-hop coloring. We also emphasize the fact that the one-hop desynchronization solution provides little interference control compared to a two-hop desynchronization solution. Now, a second motivation for studying the two-hop desynchronization problem comes from related work. In this uncoordinated task setting, there has only been 2 previous studies. One by Carnejo and Kuhn focuses on the one-hop desynchronization problem, and the second by Affectal focuses on the one-hop MIS problem. Now, all other results in the beeping model assume a stronger communication setting. So a natural question is, can two-hop desynchronization be solved in the uncoordinated task setting? Or can any two-hop problem be solved in this setting? And the main obstacle for this is, can a node communicate information to its two-hop neighbors in this setting? Interestingly, this obstacle does not exist in the global clock setting. In the global clock setting, it is simple for nodes to implement a two-hop beeping primitive. So if nodes have access to a global clock, we assume that nodes wake up at the same time, and then they separate rounds into phases of odd and even rounds. A beep in an odd round is said to be a source beep. A beep in an even round is said to be a relay beep. And now, nodes can simulate an algorithm with two-hop beeps and two-hop listens by using phases of 2 rounds in which they just beep normally. To do so, they do the following. To two-hop beep, a node beeps in both rounds of one phase. To two-hop listen, the node listens in the first round of the phase. If it hears a beep, which is a source beep, then it will beep in the phase's second round, which is a relay beep. Otherwise, it just listens again. And the two-hop listening node will hear a two-hop beep if and only if the node hears a beep in any of the 2 rounds. For this two-hop beeping primitive to work, it is important that nodes distinguish between source and relay beeps. Otherwise, nodes could relay beeps indefinitely and thus propagate beeps beyond distance 2. So naturally, one can ask, can a node implement source and relay beeps in the uncoordinated task setting? More generally, one can ask, can a node communicate non-trivial information to its neighbors in this setting? By non-trivial information, we mean letters from some alphabet of some size bigger than 2. For source and relay beep, we're just asking for an alphabet of size 2. And now, known techniques do not work in this uncoordinated task setting. They cannot answer this question. This is because phase-based techniques rely crucially on the fact that different nodes have synchronized local round numbers, which is not the case in the uncoordinated task setting. In this work, we show that we give positive answers to these questions. We showed that nodes can communicate non-trivial information, even in the uncoordinated beeping model. And we showed that two-hop desynchronization is solvable in this model, under the condition that nodes have knowledge of some upper bound on the maximum degree delta. Now, in this third part, we will show how nodes can communicate non-trivial information in the uncoordinated beeping model. In our approach, nodes use communication schemes to communicate complex information. Communication schemes are binary words of some length L that indicate how a node should communicate during L consecutive rounds. In the example below, we give to a node some communication scheme 100-101, which means that the node will beep in its first round, then it will listen in the next 2 rounds, and it will beep, listen, and beep again. In this part, we will provide communication schemes that allow nodes to communicate non-trivial information in the uncoordinated task setting. To do so, communication schemes must deal with 2 important issues. The first one is interference, and the second one is lack of coordination. The interference issue comes up from the fact that beeps naturally suffer from interference, and the lack of coordination issue comes up from the uncoordinated task setting. To deal with these 2 issues, we used a code-based approach. To present our approach, first we need some definitions. We define the bitwise OR superposition of words x and y as the word z, such that its ith bit is 1 if and only if the ith bit of x or that of y is 1. This operation generalizes to arbitrarily many words. We say that word x is contained in word z if, for each bit, if it is a 1 in x, then it is also a 1 in z. For word x and integer t, which is said to be the shift, we define the shifted word sigma xt as follows. If t is negative, we remove the first minus t bits, and then we add minus t0 bits at the end of x. In the example below, we take x, we shift it by 1 bit to the left, we remove its first bit, and we add a 1 bit to the end of x. If t is positive, we do the opposite. In the example, we take x, we shift it by 1 bit to the right, we remove its last bit, and we add a 0 bit to the beginning. Now, with this definition of shifted words, we can define a more complex superposition operation, the uncoordinated superposition. The uncoordinated superposition of a set of word and shift pairs is the superposition of the corresponding shifted word. In the example below, if we take a set x minus 1, x1, then the uncoordinated superposition of that set is the superposition of the shifted words sigma x minus 1 and sigma x1. Now, let's go back to communication schemes. Communication schemes allow nodes to communicate complex information by beeping over multiple rounds. We say that a node transmits some communication scheme starting in some round R. Now, if multiple nodes transmit schemes at the same time, then we'll have interference issues. More precisely, from the viewpoint of a listening node, if two of its neighbors transmit a communication scheme starting in the same round, then that listening node will hear the superposition of these communication schemes. This is why we define the following coordinated transmission scenario, which takes into account this interference issue. In the scenario, V and several neighbors transmit code words of some length L, starting in the same global round. This set of code words is of cardinality of at most 8, and the scenario has some conflict parameter, which bounds the number of different code words transmitted within the one-hop neighborhood. Now, the history of node V from round RV to RV plus R minus 1 is the R superposition of all code words transmitted in the one-hop neighborhood of V. We say that C, the code C, solves the scenario if V can deduce from its history which code words were transmitted in its one-hop neighborhood. To solve the coordinated transmission scenario, we can use superimposed codes. These codes were introduced in a work by Katz and Singleton in 1964, and they satisfy a superposition property. This superposition property states, for some parameter k, that every superposition of at most k code words does not contain any other code word. That means that if we take a superimposed code with some parameter k which is bigger than the conflict of a scenario, then that code solves the corresponding coordinated transmission scenario. In other words, we can use these code words as communication schemes under the condition that nodes always transmit in a coordinated manner. This condition is obviously unrealistic in the uncoordinated star setting. This is because nodes may have arbitrarily different local round numbers. Instead, if we want to use communication schemes in the uncoordinated star setting, then we need to deal with complex superpositions of communication schemes. Basically, we need to deal with uncoordinated superpositions. Now, this is why we define the uncoordinated transmission scenario, in which we take into account both the interference and lack of coordination issues. In this scenario, we have node V and several neighbors still transmitting code words, but now starting in arbitrary rounds. Here, the conflict parameter bounds the number of different code word transmissions started in a certain time interval. And for any node V, any local round RV, the history of node V from round RV to RV plus R minus 1 is the uncoordinated superposition of some codeword and shift pairs, such that the codeword was transmitted in the one-hop neighborhood of V within L-1 rounds of GVRV, and the shift depends on the starting global round of the transmission. We say that the code C solves the scenario if V can deduce from the history from RV to RV plus L-1, which codewords were transmitted in its one-hop neighborhood starting exactly in GVRV. Notice that for this scenario, even if we're asking for a single codeword, solving it is not trivial. And this is because if we have some uncoordinated superposition of a set of codeword and shift pairs in which the codeword is always the same, it is actually still a superposition of many different shifted codewords. To solve the uncoordinated transmission scenario, we introduce a new type of codes, uncoordinated superimposed codes, which extend superimposed codes. These codes satisfy a stronger superposition property, stated as follows. If we take an arbitrary set of at most k codeword and shift pairs, then the uncoordinated superposition of that set contains some codeword C prime, if and only if the codeword and shift pair C prime 0 is in the set. One can see quite easily that if we take such an uncoordinated superimposed code with parameter k, which is bigger than the conflict of the scenario, then the code solves the uncoordinated transmission scenario. Now, this is just a definition. It does not mean that such codes exist, and this is why in our work, we provided deterministic explicit constructions for such codes. This construction relies on the construction for seeded sets. I will not go into the details for that, but I just want to emphasize that this construction is not very costly in computation time. To sum up this third part, we give communication schemes that communicate non-trivial information in the uncoordinated beeping model. These communication schemes are a bit expensive and scale pretty badly. However, we can use two such communication schemes to implement source and relay beeps. This is what we will use in this fourth part to implement a two-hop beeping primitive and to solve the two-hop desynchronization problem. The two-hop beeping primitive presented here will have the same, will be along the same lines as the two-hop beeping primitive in the global clock setting. Instead of using phases to implement source and relay beeps, we'll use communication schemes to do that. And we'll add an extra condition. A node can two-hop beep at most f times within a certain period of time. Now, this two-hop beeping primitive will guarantee us that two-hop beeps are correctly transmitted with some delay. Now, more precisely, nodes know some construction of USI-Codes, and they know some upper bound in the maximum degree. So nodes will compute locally the same uncoordinated superimposed code. C1, C2, C1 is used for source beeps, C2 is used for relay beeps, and this code will be computed with a parameter k, which is equal to f times delta up plus 1 squared. This means the code words will have length of the order of delta up to the power of 4. Now, the two-hop beeping primitive is in essence simple, but it needs to take into account the fact that communication schemes are transmitted over multiple rounds. Node V, the two-hop beeping round RV, will transmit C1 starting in RV. Otherwise, if node V wants to listen to two-hop listen in round RV, then it will first check if C1 is contained in its history from round RV minus L to RV minus 1. If that is the case, V transmits C2 starting in RV, that is, it sends a relay beep, and otherwise V just listens in round RV. And this two-hop beeping primitive guarantees that for some node V in some round RV, then for any round RV prime, which is more than RV minus 2L, V hears the two-hop beep in RV prime, if and only if C1 is contained in its history from RV prime to RV prime plus L minus 1, or C2 is contained in its history from RV prime plus L to RV prime plus 2L minus 1. Here we can see that this RV prime value precisely takes into account the fact that there is a delay in the two-hop beeping primitive. We also have this following technical lemma that states let's say that in the 2-hop beeping primitive, for any node v and round r v, there are at most f times delta plus 1 squared codeword transmission started with an L minus round rounds of GVRV. This is because there is at most f times delta plus 1 source beeps started in that time period in the 1-hop neighborhood of v, because of this extra condition that the node cannot transmit more than f source beeps within a certain time period. And we can also bound the number of relay beeps started in the 1-hop neighborhood of v. I will not go into the details of exactly how we bound the number of relay beeps. Now that we have this technical lemma, we can see that if we take some code C1, C2 that solves the uncoordinated transmission scenario with a conflict of f times delta plus 1 squared, then the 2-hop beeping primitive that uses that same code is correct, because it will be able to decode all codeword transmissions thanks to this technical lemma. Now that we have the 2-hop beeping primitive, we can solve the 2-hop desynchronization problem. Coordination could present a 1-hop desynchronization solution, which is randomized and terminates correctly within delta times log n rounds with high probability. In our work, we show how to obtain the first 2-hop desynchronization solution by combining this known solution with our 2-hop beeping primitive and taking into account the fact that there is a delay for these 2-hop beeps. The resulting solution is randomized and terminates correctly within delta to the power 4 log n rounds with high probability. To sum up, we show in our work that nodes can communicate non-trivial information even in the uncoordinated beeping mode. We do this by using complex communication schemes that are based on uncoordinated superimposed codes. Using these communication schemes, we provide a deterministic 2-hop beeping primitive under the condition that nodes have an upper bound on the maximum degree delta. This allows us to obtain the first randomized 2-hop desynchronization solution in the uncoordinated start setting. And actually, this 2-hop beeping primitive is quite general. One could use it to translate a 1-hop MIS solution to a 2-hop MIS solution. Finally, although we do not present it here, we show in our work how to use a 2-hop desynchronization solution to implement a general, convenient, and efficient message passing abstraction layer. As for open question, in the first time one can ask whether one can get a faster 2-hop desynchronization solution. There is a lower bound of delta squared plus log n rounds, and the current upper bound is of the order of delta to the power of 4 times log n rounds. So can this gap be reduced? One can also ask, can nodes communicate to their 2-hop neighbors without any knowledge of the communication graph in the uncoordinated start setting? By that I mean, without this upper bound on the maximum degree, can nodes still communicate to their 2-hop neighbors? One can ask, under the same assumptions, a stronger question: can nodes synchronize local clocks? A positive or negative answer to this second question would extend both our results, but also a second result obtained in Burman recently, which solves clock synchronization in the uncoordinated start setting under the condition that nodes have some knowledge of an upper bound on the number of nodes. Thanks for listening to this presentation, and if you have any questions, feel free to contact me.